Hello everyone, this is Nasreddine Belbachir, a PhD student from the University of Mostaganem. I hope you will find our work interesting, which is titled of Analysis Impact of Multiple Distributed Generation Integration in Medium Voltage Distribution System on the Overcurrent Protection Relay Performance considering hourly uncertainties of photovoltaic power source and demand response. In these outlines, it is mentioned the main sections of our work, starting from the introduction, then talking about the overcurrent protection relay, also the load demand uncertainty and output power of distributed generation, of course, test systems, results and discussion, and finally the conclusion. Starting by the introduction. Photovoltaic power systems are gaining importance as distributed generation of renewable energy sources due to abundant availability of solar radiation as a source for generating electricity by the photovoltaic effect in semiconductors. Hence, assessing the impacts of DG on the reliability of distributed power system is an important and challenging topic. The impacts of DG can be generally classified into three categories as technical, financial, and environmental impacts. The integration of DG in existing DPS is beneficial in many technical aspects, therefore reduces power loss and at the same time improves voltage profile by keeping the bus voltage in the limits, but also the DG may produce several negative impacts. In this paper, models of uncertainty of parameters in modern power systems, such as uncertainty models of load demand and PV energy, where the main objective here is technically, which is analysis of the impacts of multiple DG units based photovoltaic sources on the directional overcurrent relay performance with considering hourly uncertainties of PV power source and electric demand response. In general, the impacts of integration of PV-DG in DPS studied in this paper are the bus voltage profile, the fault current, the overcurrent relay operating time, and the coordination time interval between primary and backup relays. In the second section of this work, we talked about the overcurrent protection relay, where the protection function is to quickly remove an element of a power system from service when it suffers fault current or when it operates in an abnormal way. The overcurrent relay is one of several protection devices used in DPS, where each part of DPS is covered by a primary and a backup overcurrent relay, and between them a coordination time interval, which its principle is mentioned in Figure 1. In past detection and clearing faults by the overcurrent relay based only on fault current. In this work, it is chosen after presence of multiple PV-DG, a type more accessible by using the measure of both fault voltage and fault current, which is the non-standard relay-based time current voltage tripping characteristic. And it is represented by its operation time equations as follow. Here we talk about the load demand uncertainty and output power of distributed generation. Starting by the load demand uncertainty, which its model is represented by the following equations. Also by doing the analysis of figure 2, which represent the daily load power demand curve, it is noticed that the maximum load power demand is from 10 to 15 o'clock. Here we talk about the photovoltaic module output power, where is dependent on the solar radiance and the ambient temperature of the site, as well as the characteristics of the module itself. And it is calculated using the following equations. The output power of photovoltaic distributed generation is mentioned in Figure 3, where it is noticed that the maximum power generated from the PV-DG is around midday. The fourth section of this work is test systems, results, and discussion. Starting by distribution line model, where the equations below are used to obtain the power flow solution in distribution line with inclusion of distributed generation units as shown in Figure 4. Figure 5 represents the single line diagram of the first test system IEEE 12 bus, which is composed of 12 buses and protected by 11 overcurrent relay. The second test system IEEE 33 bus is mentioned in Figure 6 by its single line diagram, which is composed of 33 buses and protected by 32 overcurrent relay. The results shown in this work are based on the location and sizing of multiple photovoltaic distributed generations illustrated in Table 1. Figure 7 represents bus voltage profiles variation for the first test system, the IEEE 12 bus, where it is clear that the bus voltage is improved after the presence of PVDG between hours 6 to 18. Also, the best results of bus voltage are obtained at midday because at this time the DG delivered their maximum power. Figure 8 represents bus voltage profiles variation for the second test system, which is the IEEE 33 bus, where it is observed also that the bus voltage is ameliorated after the presence of PVDG, and especially when the DG provides their maximum power at midday, as previously mentioned. In Figure 9 is mentioned the fault current variation for the first test system for cases before and after the integration of PVDG. Also, the difference between them is mentioned in Figure 10. The obtained results proves that the integration of multiple photovoltaic distributed generation has a great effect on the fault current levels, where this last is increased due to the proportional relation between it and the bus voltage. In Figure 11 is mentioned the fault current variation for the second test system for both cases before and after integration of PVDG, and the difference between them is mentioned in Figure 12, where the same remark is that the fault current is increased due to the proportional relation between it and the bus voltage, and it is proved by having the best results, the same as the case of bus voltage at midday as previously mentioned. Figure 13 represents the primary overcurrent relay operation time variation for the first test system, where it is observed after the presence of multiple PVDG into DPS that the operation time in almost all of the primary overcurrent relays is decreased due to the inverse function between the fault current EF and the fault voltage magnitude measured that covered by the overcurrent relay and its operation time, as mentioned in the previous equation. Figure 14 represents primary overcurrent relay operation time variation for the second test system, which is the IEEE 33 bus. Also, the same remark here that after the integration of PVDG into DPS, the operation time is decreased almost in all of the primary overcurrent relays. Figure 15 represents the coordination time interval variation for the first test system. It is noticed after the integration of PVDG sources in presence of non-standard overcurrent relay that there was direct impact by decreasing the CT under a minimum limit value of 0.25 seconds and leading to miscoordination. Figure 16 represents the coordination time interval variation for the second test system, which the same remark is after the integration of PVDG into DPS. The CT is decreased under the minimum limit value of 0.25 seconds and led to miscoordination between primaries and backup relays. Finally, the conclusion. In this paper, an analysis was done to study the impacts of multiple distributed generations based on photovoltaic panel considering load demand and distributed generation power output variation at different hourly on the overcurrent relay performances resumed in the fault current, the operating time, the coordination time interval between primary and backup relays, as well as the impacts on the bus voltage profiles variation of the two standard DPS test systems. The study revealed that there is a proportional relation between uncertainty of PVDG and load demand in 24 hours and the obtained results, where there was no impacts in hours between 9 to 5 a.m. as long as there was no injection of power from PVDG. Meanwhile, when presence of multiple PVDG during the rest of the day's hours, it is noticed a positive impact by ameliorating the technical studied parts by improving the bus voltage profile variation, raising the fault current levels, and reducing the operating time of overcurrent relay. When in the other side, a negative impact in minimizing the coordination time interval and leading to miscoordination between primaries and backups over current relays. The research results are hopeful to the construction of a protection system in the DPS. The optimal planning has its importance in improving overall performance of the system for getting the best possible potential from the PVDG sources and predicting the negative impacts like the miscoordination as previously mentioned. Finally, I thank you for your attention.